We are now going to start a new chapter on atoms and elements. To start this lecture, we will talk about the elements, bringing that into discussion about the periodic table, and lastly, rounding it out by talking about atoms and the components of an atom. In the previous lecture, we talked about how matter can be classified into two big categories of pure substances and mixtures. And within pure substances, we can also divide it into either being an element or being a compound. And remember that we said an element is something that cannot be broken down into a simpler substance. It is basically the fundamental building blocks of life. And we have talked about elements even before this lecture because, to be honest, you can't talk about chemistry without talking about an element. And you have also seen something in your chemistry class that looks like this, a periodic table, which lists all the elements known to us. So hopefully this discussion is not going to be something brand new to you. So humans have known about elements for a very long time. Going back to ancient times, we already know about precious elements like gold or silver. So these elements tend to have older names, whereas newer elements have been discovered within a couple hundred years, and they tend to have the same ending in their names. For example, aluminum was successfully discovered in the 1800s, and it was named after the alum that it is made from, or it could be named after a famous scientist. For example, a very radioactive element known as curium is named after the chemist who studied radioactivity, and in the 1900s, her name was Marie Curie. Or it could be a new element like titanium, which is a very strong element, and so it was named after a Greek mythological character known for strength. And I can go on because there are 92 more elements that we know up until this point. And because there are so many elements and we want to be more succinct when we write them, we have come up with a way to shorthand them in what we call the chemical symbols. So basically it is a code name for each of the elements. It starts with a capital letter and either is one or two letters long. So for example, hydrogen is symbolized by the letter H, and helium, since helium also starts with H, we must find another letter, so they decided to pick H and lowercase e to stand for helium. It is important to indicate and write clearly whether something is capital or lowercase when you talk about chemical symbols, because, for example, between uppercase C, uppercase O versus uppercase C, lowercase o, they mean different things. The first case is carbon monoxide, which is a compound of carbon and oxygen, while the second case, uppercase C, lowercase o, is the element cobalt. So let's take a look at some more elements that you should be familiar with. Again, you do not have to memorize all these elements on a test. You would be provided with a periodic table with the symbols and the name of these elements, but you should be familiar with it enough so that on the test you are not wasting too much time searching for it. So let's talk about some of these elements and how they got their chemical symbols. Some elements are straightforward, like aluminum starts with Al, so its chemical symbol is Al, or argon, which is Ar. But then when you go to arsenic, it also starts with Ar, so we can't use Ar again, so we go to the next one, so its symbol becomes As. And then there are chemical symbols that totally would not make sense to us nowadays. For example, copper is not abbreviated Co, but abbreviated Cu, and it's because it comes from its older name, cuprum, which is related to the country Cyprus, because in antiquity, copper was found mainly on the island of Cyprus in the Mediterranean Sea. You will see many symbols like this where the symbol is derived from the older ancient names of the element. Some more examples include gold, Au for aurum, iron, Fe for ferrum, lead, Pb for plumbum, mercury, Hg for hydrargyrum. I don't know. I have no idea if I said that word correctly. A note of interest here, if you break up that word, hydra means water and gyrum means silver. So mercury literally means liquid silver. You may have heard the term quicksilver. It's also talking about mercury, because remember that mercury is the only metal that is a liquid. So you have mercury as liquid silver, and then you have silver here as argentum, abbreviated Ag. Potassium is K from its old name of kalium, or sodium, symbolized Na from its old name natrium, and so on and so forth. The take-home message here is to get familiar with all these elements and where they are on the periodic table, but you do not have to memorize them. Now let me give you a trivia question. Is diamond an element? Gold is an element, right? Silver is an element. Is diamond an element? So this is a little bit of a tricky question. Diamond is indeed not an element. It is, however, the elemental form of carbon. And I want to highlight this one slide to talk about carbon because it is a very precious element for life. And that's not because diamonds are made of carbon. That is just one interesting aspect of carbon. The way carbons are organized in a certain way can give you something like diamond, or if it's organized in another way, it can give you something less expensive like graphite. But again, the main reason why carbon is so precious to life is not in its elemental form, but in its compound form. Because carbon can bind to so many other elements, it can form so many different types of molecules that are important to life, like carbon dioxide, like the enzymes in your body, like your DNA, like the carbohydrate, the protein, the fat that sustains life. So carbon is so special of an element that at the end of the semester we will spend one whole chapter talking about the chemistry of carbon. And if you're really interested, you can spend a whole year learning the chemistry of carbon in what is known as organic chemistry. But for now, let's leave it as that. Okay, so we come to our first checkpoint. And the question asks, identify the elements that is found in amoxicillin, C16H19, N3O5S. Okay, so this is a molecule or a compound. All right, so hopefully you said the answer was A because C stands for carbon, H stands for hydrogen, N stands for nitrogen, O stands for oxygen, and S stands for sulfur. All right, so let's go back to the idea that there are so many elements. It turns out that many elements also have very similar attributes, very similar characteristics to one another. So we need to find a way to organize them and see what kind of patterns emerge. This is what Dmitry Mendeleev, a Russian scientist, thought about when he first proposed something called the periodic table. So to think about what he did, let's imagine if you have a bunch of blocks here, and these blocks have some characteristics that are similar to each other, and they have numbers associated with them. So one thing we can say is, why don't we just line them up in order and see if there are any patterns that emerge? So if we do that, we can see that the first number is a square, can go first, followed by number 2, which is a circle, then number 3, which is a diamond, then number 4, which is a triangle, and so on and so forth, 5, 6, 7, 8, and 9, and 10. And what we notice is that the pattern repeats after a while. It starts with a square, a circle, a diamond, and a triangle. Then it goes back to a square, a circle, a diamond, and a triangle, and so on and so forth. Because there's a pattern that repeats like that, we call that pattern being periodic. Now this pattern is so strong that even though we don't know what shape number 11 would be, we can actually make a guess what it could be. What do you think the shape of number 11 would be? You would be correct if you said, and this is actually very similar of an idea to what Mendeleev based his periodic table on. So let's go back to the elements. Back then, not all the elements were actually known, but the elements that they did know, they did see some kind of pattern. So for example, if we color-coded the characteristics of an element by color, what we see is that if we line them up by their side, which is symbolized by the numbers on top of these elements, that there is a strong pattern that emerges. That there's going to be a peach, then a green, then a blue, then a purple element, followed by some white elements, then again a peach, a green, a blue, a purple, white elements, peach, green, blue, and purple. If we say that at every time it repeats a pattern, we indent it and makes it go down to another row, we then have basically formed the first simple periodic table. And in this periodic table, what you see stand out is that every element that has similar characteristics will then fall into one column. All the blues fall in this column, all the purple fall in this column, peach and green, etc. Because the similarities are so stark, we also call these groups family. All right, let's zoom out and take a look at the modern periodic table and discuss some aspects of it. As previously discussed, elements on the same column are sometimes called families or groups. Each group also follows a number system. For example, this group is called group 1A, this group is called group 2A, 3A, 4A, 5A, 6A, 7A, 8A, for example, and each rows represent a period. On the periodic table, you can also see elements divided into two groups. The first group is called the main group and is signified by the letter A, and the A designation follows the group number. And then there are the transition metals, which is signified with the letter B. The transition metals are in the middle of the periodic table. Again, the group number would be 3B, 4B, 5B, so on and so forth. Now, on top of these 1A or 3Bs, you can also see another numbering system which starts from 1, 2, 3, all the way to 18. This is different from the lower number, which has a counting system that skips the transition metals altogether. As you can see here, it goes from 1A to 2A and jumps to 3A and 4A. Now notice that the numbers on top continue to increase one number at a time. For example, you can see this is 39, 40, 41, so on and so forth. But notice if you go down here, starting at 57, you see that it's next to it is 72, right? So there's a bunch of numbers that was skipped. Same thing here, 89, and the next number was 104. So there actually is a lot of elements in between that couldn't fit into this periodic table. And these elements are called the lanthanides or the actinides. These elements we will not see very much often anyways, except when we're talking about nuclear chemistry. Okay, so what kind of questions can be asked of you from this periodic table? For example, I can ask you what element is in group 2A and is on period 4. And so you can say group 2A is here, period 4 is here, so that is calcium. In addition to the group numbers, some special element families also have names. For example, calcium we just saw belongs to group 2A, which has a family name called the alkaline earth metals. Next to the alkaline earth metals are alkali metals. Over to the right hand side of this periodic table, we skip over this region where there are no common names for until we go to group 7A, and they are called halogens, and then lastly 8A are called noble gases. The elements in the middle are called transition elements. Let's emphasize again why these elements are in their family. And one of the reasons is that they have common characteristics. For example, in group 1A, the alkali metals, they are very reactive to water. So for example, if you put lithium in water, it will start to react with water, and you see this reaction as sizzling. And if you put sodium in water, that same reaction occurs but a little bit more violently, and this level of violence increases as you go down the list. Similarly, for group 7A, the halogens, their common characteristic is that they are all, for example, diatomic molecules, and that's a term we'll learn about later on. That just means they have two atoms for every molecule, like chlorine, two chlorines, bromines, and iodine, and they're often gases at room temperature. Now before we move on from the periodic table, let's discuss another pattern in the periodic table. In the periodic table, we can also divide elements into metals versus nonmetals. On the left, color-coded here in blue are the metals, whereas on the right, color-coded in yellow are the nonmetals. In between is a zigzag step ladder of elements that has some characteristics of metals and some characteristics of nonmetals. So they are called the metalloids. Let's take a look at how we can distinguish some characteristics between the metals, the metalloids, and the nonmetals. Some characteristics of metals are that they are solid at room temperature, they are shiny, they are ductile, meaning you can bend them and form different shapes out of them. They are conductors of heat and electricity. And an example here, as you see, is that from that top picture there of gold coins. And now let's compare that to metalloids and nonmetals. Our prime example of a metalloid here is this block of silicon, whereas nonmetal is this block of charcoal, which is carbon, and this bottle of chlorine gas. Alright, so going back to metals being solid, nonmetals don't have to be solid. Some of them are solid like the charcoal, but some of them are gases like the chlorine gas. Whereas metalloids are going to be solid. What about the shininess? Well, nonmetals are going to be dull, are going to be not very shiny, whereas metalloids still have that metal-like property of being shiny. Metalloids are ductile, while nonmetals are often brittle. That means they break. It's hard to form shapes out of them because they do break. And lastly, nonmetals are insulators. That means they don't conduct heat or electricity very well. And metalloids are semiconductors, so they are in between. They can conduct up to a certain extent. Let's take a look at the elements that are found in our body. It turns out we are composed of mainly 4 elements. We are made up of 96% of these elements. Can you guess what these elements are? They are oxygen, carbon, hydrogen, and nitrogen. So good for you if you notice that these are all nonmetals, and we indeed are made of nonmetals. But we actually are made up of some metals also. So as I go through this list, why don't you challenge yourself by seeing if you can name the elements before I tell you the name of the element, and you can find them on the periodic table. So the first macro mineral we can find in our body, that's something that's very important for bone and teeth health. Its chemical symbol is Ca. It's calcium. Next, this element is important in ATP, which is the energy currency in biology. Its chemical symbol is P. Yep, it is phosphorus. This next element is important as an electrolyte. It allows for muscle contraction and nerves impulses to occur. Symbolized with the letter K is potassium. The next element is important for fluid balance because it exists as a negatively charged ion. It's also found in your stomach acid, HCl. Its chemical symbol is Cl. It is chlorine. The next element is found in proteins where it makes sulfide bonds that are very important for the shape and function of that protein or enzyme. Its chemical symbol is S. That is sulfur. Next, we have another electrolyte that is very important for water balance. Chemical symbol is Na. It is sodium. And finally, we have an element that is, again, good for bone health. It is a cofactor and very important in metabolic reactions. Its chemical symbol is Mg. It is magnesium. And then there are a lot of trace elements that you need, and they are also called microminerals. For example, Fe, iron, Si, silicon, Zn, zinc, Cu, copper, Mn, manganese, and so on and so forth. There's a lot. Alright, good. So hopefully that provided you some practice in looking up chemical symbols and names. Checkpoint. Can you identify the group of elements below that contain only halogens? Great, if you said B, bromine, chlorine, fluorine are all halogens. Before we move on, let's have a element joke. If you can't helium or curium, what are you going to do? You're going to barium. So remember we said that elements cannot be broken down into simpler substances and that they're fundamental building blocks. So then what is an element composed of? This is a central question that is very important in chemistry. To get an idea what an atom is, imagine tearing this piece of aluminum in half and then tearing it in half again and again and again until you get to the very, very tiny piece where you cannot tear it in half anymore. That piece that still maintains the characteristic of the element of aluminum, we call that the aluminum atom. The definition of an atom is defined as the smallest particle of an element that retains the characteristics of that element. How small is an atom, you may ask? This is so mind-boggling that to give you an idea of how small the atom is, imagine holding a clump of sand in your hand. Now zooming in into that one grain of sand, and sand is made out of silicon atoms. In that one grain of sand, how many silicon atoms do you think there are? This is how many atoms there are. Can you even say that this number? That's 50 million atoms. That's how small it is. Only at this magnitude can we actually visualize the atoms. Mind-boggling, right? So the theory of atoms is relatively new, within a couple of hundred years only, but the concept have actually been around for thousands of years. It first started with the idea from a Greek philosopher named Democritus, and he made his idea from observing that if you take a piece of rock and you divide the rock in half, each half of the rock still has the characteristics of that rock. And if you do that again and again and again, where you cannot do that anymore. And at that point, he called it an atomos, which means cannot be divided any further. Another famous philosopher at the time is Aristotle, and his idea was opposite of Democritus. His idea was that matter is infinitely divisible, that it's actually made up of components of air, fire, earth, and water. And it turns out at that time Aristotle was a big philosopher. He had a lot of great ideas, and because he had a lot of great ideas, people tend to believe whatever he thought too. So Democritus's idea was pushed aside, and for 2,000 years, Aristotle's idea was what was accepted as the truth. Not until more than 2,000 years later, when in Europe came the scientific revolution, when people had the ability to test and try out theories, and not just by philosophy, was Democritus' idea reemerged. Primarily, it was reaffirmed by John Dalton, who came up with an atomic theory, in which he outlines that 1, all matter are made of tiny particles, and he called it atoms. Number 2, that all atoms of an element are unique. That means that all the atoms of chlorine are all the same, but they are different from all the atoms of oxygen, which again are all the same within oxygens. Number 3, atoms combine to form compounds, and they combine in a ratio that is always fixed. So for example, water will always have 2 parts hydrogen and 1 part oxygen. And number 4, atoms are never created nor ever destroyed, but they can recombine in a chemical reaction and form new compounds. And most of Dalton's ideas since then have been accepted with some minor tweaks. Like for example, in his second statement, it turns out that atoms of the same element are not all identical, as we will see later on. And even though an atom is defined as something that is not divisible, it is actually made up of smaller particles, and those smaller particles are called subatomic particles. Subatomic meaning smaller than the atom itself. So what actually makes up the atoms? So now we know that atoms are composed of a positively charged particle called protons, and we abbreviate that with a P positive sign. It is also composed of a negatively charged particle called the electron, symbolized by E and a negative charge. And lastly, it also has a particle that does not have a charge, and this particle is called the neutrons. These subatomic particles were actually discovered because of their charged nature. To talk about how they were discovered, let's talk about a concept that likes will repel another and opposites will attract. So for example, when you have 2 positive charges here, they will repel one another, or when you have 2 negative charges, they will repel one another. But if you have a positive and negative, they are attracted to one another. The discovery of the electron was found by J.J. Thomson, where he was able to produce a stream of small particles called a cathode ray, which are basically electrons through a glass tube, and he found that these electrons were attracted to the positive electrode, and because of that, he knew that the subatomic particle of electrons were negatively charged. He also knew that the atom was a particle that was overall neutral, so to counterbalance this negatively charged species, there must be something else that was positively charged, so we call that the protons. So from these 2 concepts, he came up with what is known as his plum pudding model. And plum pudding is an old English dessert, so we may not find it very intuitive. You can also think about this as a chocolate chip cookie, where the atom is a cookie and is positively charged and is sprinkled with these chocolate chips or these plums in this pudding. And these chocolate chips or plums are the negatively charged electrons. Now, one of his students came along and wanted to test his idea of a plum pudding model for the atom. This student was Ernest Rutherford. One of the key consequence of the plum pudding model is that the atom is mostly made up of empty space with tiny electrons sprinkled without. So if you were to throw particles at this atom, most of the particle will go straight through because the atom, again, is made up of empty space. So in his experiment, he set up a beam of positively charged particles and shot it at a thin gold foil, which is made of gold atoms. If Thomson's theory were true, then all of these positively particles will go straight through to the other side. But in fact, Rutherford shockingly discovered that some particles did go straight through, but not all. Some of them actually reflected in different directions, even shot directly back at the source. And because of this, there is a very dense core that has mass so that the positively charged particles does bounce back. And this densely charged center of the atom is made up of protons. And so we call this the nucleus of the atom. And with further experimentations, we now know that the electrons reside on the outside of the nucleus. So let's talk about the mass of the atom, which is, remember, a very, very small particle. So the unit must be very small too. So for example, a proton weighs 1.67 times 10 to a negative 24 grams. That's a very, very small amount. It's not very useful for us. So instead we use a different unit called the atomic mass unit, AMU. And we have defined it so that one proton is 1.007 AMU, or basically 1 AMU. And turns out protons and neutrons weigh very similar to each other. And electrons, however, are very, very light. It is 0.0005 AMU. It's very small. So small and negligible that when we talk about the mass of an atom, we just say that it is composed of the mass of the protons and the mass of the neutrons. Okay, now let's have a summary and talk about what we now know about the atoms. We know that it is made up of subatomic particles called protons, neutrons, and electrons. The proton is symbolized with a P with a positive sign because it has a charge of positive 1. It also has a mass of 1 AMU and is found within the nucleus. A similar particle is a neutron. However, a neutron does not have a charge, but it does have a mass of about 1 AMU and also lives in the nucleus. Whereas an electron, symbol E negative sign, because it has a negative 1 charge, does not have much weight, basically 0, and is found outside of the nucleus. Okay, let's go to a checkpoint. Which of the following statements about atoms is not true? Pause and read your options. Hopefully you said an electron has a larger mass than a proton is false. An electron is the smallest of the subatomic particles. Okay, quick joke here. A neutron walks into a bar, says, "Bartender, how much for a beer?" Bartender says, "For you, no charge." Okay, let's end this lecture with talking about atomic number and something called mass number. So as we said, each element is assigned an atomic number, and that atomic number is very unique to it. That atomic number represents the number of protons it has. You may see these atomic numbers written on a periodic table. That's the number that's on the top of the chemical symbol for each element. So for example, for lithium, the number on top is 3. So its atomic number is 3. That means it has 3 protons. Carbon is atomic number 6, whereas mercury is atomic number 80, so 80 protons. Now if you are talking about an atom and not an ion, you know that an atom is something that is neutral. Neutral means it has a net charge of 0. The positive and the negative charges will cancel out. And what are positive and negative in an atom? Right? The positive is the proton, the negative is the electron. So if you're an element that has 2 protons, to be a neutral element, you also must have 2 electrons. Because positive 2 plus negative 2 is equal to 0. So this is why, in order to count electrons of an atom, is basically the same number of the protons, which is the atomic number. So, for example, how many electrons do these atoms have? Lithium has 3 protons, so it also has 3 electrons. Carbon has 6 protons, so it also has 6 electrons. Mercury has 80 protons, so also 80 electrons. Now let's talk about the mass in an atom. Can you recall what we said is the massive part of an atom? Which subatomic particles has mass? Right? Protons and neutrons are the only one that has mass. So when we talk about a mass number, it's just the contribution from the proton and neutron. And remember, the proton and neutrons both have 1 AMU of mass. So the mass number is just to add the numbers of proton you have with the number of neutrons you have. Now as a note, this number is not found on a periodic table. It must be given to you in another way. So for example, if I say that a nucleus of a hydrogen contains 1 proton and 1 neutron, what is its mass number? Right? That's 1 plus 1 is 2. Its mass number would be 2. How about this? If a particular sulfur atom has a mass number of 35, how many neutrons does it have? Okay, so we know that sulfur is atomic number 16, so it has 16 protons. In order to calculate the number of neutrons, you take that minus it from its mass number. So it's 35 minus 16 is 19. And that's how you calculate mass number. Final checkpoint here. An atom of calcium has a mass number of 42. Identify the number of protons, neutrons, and electrons it has. Calcium is atomic number 20, so it has 20 protons and 20 electrons. Number of neutrons is calculated from the mass number minus its proton count. So 42 minus 20 is 22. Answer is B. Very good. So by the end of today's lecture, you should be able to do the following thing. You should be able to, given the name of an element, write its correct symbol, and then vice versa. You should be able to use the periodic table to identify the group and the period of an element, and identify the element as a metal, a nonmetal, or a metalloid. You should be able to describe the electrical charge and locations of the subatomic particles. And given the mass number of an atom, state the number of subatomic particles it has.